In this video, we're going to continue our discussion on calculating zeros of polynomial functions. So to calculate zeros, we're going to use Descartes' rule of signs. We're going to use the rational zero test. We're going to test these rational zeros. Okay? And we're going to use the fact of upper and lower bounds to eliminate possible zeros. And we're going to factor as a product of linear and irreducible quadratic factors. Okay. All right, so for the following problems, we're going to be doing these four things here. Okay. So let's look at our first polynomial function equation. So possible positive and negative real zeros, we're going to be using Descartes' rule of signs. So possible positive reals, that's the number of sign changes. So here to here has a sign change of 1, and that's it. So 1. So possible negative reals. So again, I'm going to do p of negative x. Remember, if the exponential power is even, nothing changes. If the exponential power is odd, it will change the sign as such. So now let's count this number of consecutive sign changes. 1 and 2 and 3. So it's either going to be 3 or 1. So now let's fill in the table for this. So possible positive reals, always going to be 1. So the first scenario is 3 possible negative reals. Because the degree is 4, that would leave us with 0 complex numbers in this scenario. The other scenario is you could have 1 possible negative real. And again, the degree is 4. So that could leave us in this particular scenario with 2 complex solutions. Okay, part B, listing all possible rational zeros. Well, that is using the rational root theorem. And again, that's the factors of the constant, which is 10, divided by the factors of the leading coefficient of 1. Since you're dividing by 1, the only thing I have to worry about is the factors of 10, which is 1, 2, 5, and 10. Okay, so now let's begin to factor as a product of linear and irreducible quadratic factors. Okay, so let's try -1 first. So put in the numbers. So what? We have bringing down the -1. So multiply, that's 1. Add, and we continue. Because the remainder is 0, we know what? X plus 1 is a factor, and -1 is a 0. Okay. Now, I'm going to rewrite this as what? -x cubed minus 3x squared plus 3x plus 10. Now, notice you do have 4 factors, but I'm not going to be able to use factor by grouping for this. So I'm going to have to do some more synthetic division and find maybe another factor. Well, let's try 2. So again, I'm going to use this row for values. Okay. All right, so let's work this. So what do we know? X minus 2 is a factor, and 2 is a 0. All right, so let's see what we now have then. We have -x squared minus 4x minus 5, which is the same thing as what? -1 times x squared plus 4x plus 5. So first of all, p of x. I can write this as x minus 2, x plus 1, and I'm going to put the negative in front so I don't forget that, and then I'm going to put x squared plus 4x plus 5 here. So this is fine because we know x squared plus 4x plus 5 is not factorable. There's no factors of 5 that add up to be 4. Okay, my zeros I can write underneath. Now, two of them I'll know very quickly because we already determined those. Now, the problem is I still need to work with x squared plus 4x plus 5. Okay, so underneath I'm going to put x squared plus 4x plus 5 is equal to 0. Now, you could either use quadratic formula or completing the square. I'm going to complete the square in this case. So we have x squared plus 4x plus blank plus 5. I'll leave a little bit of room is equal to 0. So half of 4 is 2, and 2 squared is 4. So what? I'm going to put plus 4 and minus 4. Okay. All right. Now, x squared plus 4x plus 4, that is x plus 2 squared plus 1 equal to 0. I'll put my squared. Subtract. Take the square root of both sides. Well, we know the square root of negative 1. That is going to be I. So then subtract the 2. Okay. So, and now I can put this back up here. I'll separate them. Negative 2 plus I and negative 2 minus I. Not only is the complex number a solution, but its conjugate is also a solution, going back to the complex conjugate theorem here. Okay. Okay, so I want to take a look at one other example with this then. Now, again, using Descartes' rule of signs, again, for possible positive reals, all I need to do is count the sign changes of the original polynomial function, and we have 1 here, and that's it. Okay. So my possible negative reals, remember that's going to be p of negative x. Again, if the exponential power is even, the term will not change whether it's negative x or positive. But if it's an odd exponential power, then the sign in front is going to change. Okay, so let's count the number of consecutive sign changes. 1, 2, 3. So it's either going to be 3 or 3 minus 2, which is 1. Okay, okay, so I've set up my table for possible positive reals, possible negative reals, and complex. Okay. So again, there's 2 different scenarios that could happen here. Okay. One possible positive real for both. First scenario would be 3 possible negatives. And again, the degree is 4, so there would be 0 complex solutions in this scenario. For the second one, I could have 1, and then what? The degree again is 4. That would leave me in this scenario to have 2 complex solutions. Okay, now, possible rational zeros. Again, we want factors of the constant, which is 12, divided by the factors of the leading coefficient, which is 1. Again, because you're dividing by 1, I just need to write out the factors of 12. So plus or minus 1, 2, 3, 4, 6, and 12. Because again, you would be dividing everything by 1. Okay, so let's start trying some of these then. Okay, let's do 1. Okay. Okay, so let's do the synthetic division for this. Notice the remainder again is 0. So what do I know? X minus 1 is a factor, and 1 is a 0. So now I want to be able to write this out to see what this looks like. So it's what? X cubed plus 3x squared plus 4x plus 12. Again, 4 terms. This problem, unlike the previous example, looks like I can factor by grouping. Well, let's check. I should be able to factor out what? An x squared here. That leaves me with x plus 3. And then from these 2 terms, I can factor out a 4. Ooh, and it's also x plus 3. Okay, so now I can write this out here as what? X squared plus 4 times x plus 3. Okay, so I'm going to write p of x here. Okay, I'm going to do my factors first. That's x minus 1. We have x plus 3 and x squared plus 4. Okay? Now again, for the zeros, two of them should be very, very quick. If it's x minus 1, the 0 is 1. If the factor is x plus 3, that is negative 3. And similarly to the last problem, I'm going to do x squared plus 4 is equal to 0. Subtract 4. Square root of negative 4 is 2i. So that will be plus or minus 2i. Now, you could write 2i comma negative 2i. That would be fine. So again, notice two real number solutions and two complex solutions. Going to back to Descartes, that scenario is the one that comes up. Other comment I would make is you can also write p of x as what? X minus 1 times x plus 3, and you could do x plus 2i and x minus 2i. Okay, last example that I want to take a look at is determine a polynomial equation with real coefficients that have the following roots. Now, your roots, 0, 4i. But you also know that negative 4i is a solution also because of the complex conjugate idea. So how do I write this as factors? Okay, so here are my zeros or my roots. Let's write these out as factors. X minus 4i, x minus a negative 4i, that's x plus 4i. Now we're just going to multiply. I'm going to multiply the sum and difference first. That's x squared minus 16i squared. But I squared is negative 1. So that's x squared plus 16. Now, what do? I'm going to multiply that by x. Okay. Now, I will write this as a polynomial function equation. I'm going to call it p of x is equal to x cubed plus 16x. Now, if you factor out the x and you do the zero product property, you would find out that the three zeros for this would be 0, 4i, and negative 4i.